Hi, I'm Tim Lambert from Dell.
I'm Phil Leech from HP.
Kasper Wszolek from Intel.
All right. We're here to talk about our love and passion out of band. You see a lot of sessions this week where there's a lot of challenges being brought up around sideband, out-of-band management. There's a ton of wonderful work happening, obviously in the security domain, into the telemetry domain, but it really comes down to the speeds and feeds. Are you getting what you think you need for the types of challenges that are coming? So we're going to go through some of the trends, and we're going to basically show kind of the state of the art of the latest challenges and what we're trying to do to help in this realm that's historically been quite eclectic and all over the place, but not necessarily differentiating for your products. So the out of band, the bandwidth is going up. The scale out or the fan out is getting pretty crazy. I don't know, 40 drive backplane is a fan out example of an interface that in the past would have been 100 kilohertz I2C, and now you're expecting NVMe telemetry. Obviously, these things aren't adding up. Telemetry from GPUs. Larger firmware images, there's certain GPU where the diagnostic images are gigabytes. There's firmware images for DPUs that are gigabytes. There's a lot of things fundamentally changing from the old days of a peripheral having a small, 100K flash or something. There's a lot of evolving boot and runtime security services as you're going through the discovery, the types of things you've seen here today around the plug and play. You're trying to understand all the couplings in the system, get very comprehensive inventory, and configure the system, as well as continued extension of the platform root of trust to all the other domains. Those don't take zero time, but time is money in the boot flow. Much more telemetry and the number of sources. Now you take all that and you multiply it by a multi-node. You see a BMC with, I think the example given earlier was a 10-node sort of situation. Now you have a 10x problem before you've even started. So what we're trying to do is focus on the common discovery and usages between the OEMs and vendors for the agreement on certain interfaces going forward to be able to make these leaps from the historical slow type of interfaces that have these sorts of challenges, like MUX blocking, getting, starving, not being able to fully utilize these interfaces at modern interfaces. The out of band can't be thought of as a secondary thought anymore. There was an earlier session on, so the interface consolidation for like the multi-node, the interface consolidation, you look at something like a DC-SCM, the connector's 168 pins. Some of these things are, okay, there's a lot of these things that really could converge to a real-time and a non-real-time. There's not really that much or true real-time. There's real-time obviously at the telemetry level, but say throttling kind of events, things that keep you up and keep the system up and handle very odd excursion situations. So the consolidation, always thinking you got a real-time interface and you got the non-real-time. Is a very important distinction because it gets muddied a lot of times on when people are choosing what to put across which interfaces. We want to harden and make more robust the security. There's a MCTP to USB binding spec. PCI VDM is a historical type of interface that, say, hyperscalers may have chosen to not use. It's basically PCI-based bandwidth for out-of-band. But there were some access control concerns. There was isolated control plane concerns. There was some reliability where the control plane can affect the data plane, like an unsupported request kind of situation, broadcast access control. So they're going to go through different areas of this where we're working through standards like PCI SIG to be able to help button up those things and to make them to be able to use the absolute best out-of-band path possible. And then sunsetting older interfaces, it's not exciting, it's hard, But I mean, we're using some of these opportunities, such as the AI boom, to be able to sort of lay down that we really can start sunsetting some historically very painful interfaces to implement that have very short distances, they're really slow, or things of that nature, as well as the flexibility of the ability to have wires that you're paying for through connectors and cables that you want to be able to reconfigure what it does based on what's on the other side of the interface. There's a big push toward this Flex IO function that's gone into the PCI spec. So we're going to go through and try not to bore you, but these are really good charts around different types of interfaces and the pros and cons, but really what we're doing to try to help them move forward.
All right, thanks, Tim. So yeah, as Tim mentioned, we wanted to dig a little bit deeper into these different interfaces. If you look at Flex IO and discrete IO, essentially discrete IO has been traditionally, sort of low fixed function, and we really want to minimize the number of discrete IOs, GPIOs as possible, or discrete special purpose signals. And really shift towards Flex IO, which is something that if you look at on the MXIO, if you look on the the PIC power, that's where these additional sideband signals are that you can configure and use for whatever you'd like to do. That's great, but sort of as we've progressed down the modular plug and play route, we've determined that maybe we need to per device class sort of come up with what the set of default Flex IO signals should be. We have a riser, and it's going to have some different needs than a backplane, and even subclass with like maybe a UBM backplane versus a legacy backplane. So some of the things we'd like to do is say, well, let's go into the MXIO spec and propose these different Flex IO defaults, and then bring that back into the MPMP to say, well, this is then how you describe, if you don't use the defaults, if you'd like to do something unique with those Flex IOs, well, then this is how you would describe it using JSON data that the BMC would collect from those peripherals, and then it would use that data to program the FPGA accordingly to support whatever the Flex IO needs are. Go next slide. Next, there's a series of single wire serial interfaces, different virtual wire, or small limited number of you've got two 4-wire interfaces such as LTPI. You can, as you can see, there's different signal. There's different bandwidths. You have PESTI, which is if you look at the MPESTI spec, that's designed to do some sort of low-level discovery and to provide a set of virtual wires. I believe it's up to 16 virtual wires that you can essentially get as sort of real-time traffic through the PESTI interface. Next, you have SGPIO, which is essentially it's basically clocking GPIO bits, however many that you want. Well, with SGPIO, we'd like to standardize that as well, and that's something we're doing in the MPMP, and that's, so you see an asterisk there. That's something that we're trying to define, how many GPIOs, what would be the sort of set of GPIOs that you'd like to have clocked there. SPI, well, that's obviously a much faster interface, and the idea with SPI is, well, yes, it's for getting your random access memory, getting to your bias or maybe your BMC images, but you can use SPI for other uses, such as connecting to the FPGA, as you can see in the diagram there, to get to sort of the memory mapped registers and additional storage. And finally, LTPI, that's an interface that, along with SGPIO, is sort of can be flexible enough to provide much higher bandwidth for not just transferring GPIOs, but doing random access as well, which is something that we see as a very sort of future-proofing interface, because it can do quite a bit. It's designed to be time division multiplex and to tunnel other things like I2C and UART, as well as having random data access and GPIO, low and normal latency GPIOs. With that, I'll pass it on to Kasper.
Thank you, Phil. So the next one is what is called right now 2 wires, but it's actually either I2C SM bus or I3C interfaces. So I2C has been used in the server platform designs for years, thanks to its simplicity, low cost, good integration with the firmware, and proliferation of parts that are supporting that. It's been used extensively to support server platforms for the use cases like through I/O expander sensors, PCIe targets, and so on, right? But there are certainly problems with in the specific use cases such as MCTP over SMBus, where there's in often cases there's a need to use a series of maxes or a hierarchy of maxes where you will be holding off the bus until the response comes back, which is creating a lot of inefficiencies in those communications. And there are some solutions in place, like I2C hubs that support agent-based communication that can offload the traffic and provide concurrent access to actually concurrent communication with all those downstream devices. So that's one of the solutions. I3C is an evolution of I2C. It adds a higher bandwidth. It adds built-in interrupt. It adds the dynamic addressing as a mandatory requirements. But it doesn't all come for free, right? There are the I2C is posing a serious challenges on the signal integrity side, on the system designers, on your routing LAN. The designer needs to look at the buffer strengths of your devices, the total capacitance of the bus, and all sorts of those aspects that they simply didn't care that much with I2C interfaces, it's eventually the bandwidth is not that high, right? The bandwidth that we are seeing in effective use cases is not delivering what's been promised. So looking at all of that, it comes into the new solutions that comes into picture are the solutions like I3C to USB bridges, where you can treat the I3C interface or I2C interface as the last inch interface on your system that allows you to connect, route the differential pairs with a USB and fan out very close to the CAM slots, to the MXIO slots, to all those I/O cards, or even on the card, right? Leverage the PCIe SIG addition of the USB interface and fan out on the card, which is a good segue to the next slide. So USB 2.0 is coming fast. It's becoming the out-of-band management interface of choice in many cases. There's a lot of industry goodness already available. All the parts that are providing bridging over USB to all sorts of interfaces like I3C, I2C, GPIO expanders, UARTs. Excuse me. And I3C is also provisioned in, as you can see on this diagram, is provisioned in most of the I/O expansion connectors and modules within the MHS. And it's also coming through the addition to the industry standard like PCIe SIG, M.2. It's supported by the DC-SCM, MXIO, OCP-NIC, and so on and so forth. So it's coming clearly. MCTP over USB is being defined. It's currently at 1.0. Excuse me. And it's so there are some inefficiencies in that definition, and we're working on fixing that in 1.1. Some of the vendors are going to implement this 1.1 specifications, which is actually addressing bottlenecks in the large topologies. So we see long-term that those topologies on the USB out-of-band management will be large, and we need to effectively leverage that for 80 megabits of bandwidth, not to waste it for polling cycles and those type of solutions. So that we are fixing that in the MTF. There's a 1.1 proposal. And obviously, you can think of the natural expansion into 3.1 and We discuss it during the summit with multiple partners here. There are certainly use cases that will require higher bandwidth, the multi-node use cases, video transport over USB from the host for KVM, and so on and so forth. So USB already has a rich portfolio of solution, and it already has a very well-defined path for evolution. So you pay as you go. You can move over to the higher bandwidth interfaces, but maintaining all the class device specification without changing a lot over generations.
Did you want to talk to this one? Did you want to talk to it? Oh, okay. Yeah, so these are basically the last couple slides, some examples of ways that you can use some of these interfaces like the FlexIO, where the left side is the source to destination. So we have a system that has 36 cables in it, and you really want to know which one, especially with things like the interoperability provided by MPIC and XIO, provide a lot of situations where things could go wrong by an assembler or a service technician. So there's a source to destination kind of mechanism we're working on in terms of the plug and play effort, where you may not need virtual wire tunneling, but you may just use it as a stimulus response kind of algorithm method. The middle one was really around random access memory. As you cross that DC-SCM boundary, you really, most of the things coming in are coming into the HPM. So do you want to shift them all into the SCM in order for the BMC to read them, or do you want to go directly to closest to the source and destination and where those come? So there's mechanisms where you can do random access memory through SGPIO we're contributing, and then as well as obviously you can do all this through LTPI, but you can also use like a SPI interface just as a very a simple byte access kind of situation. And then peripheral USB discovery. So PCI Chem has added this. It took a while, but it's you could ask, well, why do I need an I2C and a or two wire bus, because it includes I3C as an option now as well, to get discovery. But I mean, so there's this. It goes into this FlexIO rules, which are in the PCI base spec released, that talk about how the different situations of break before make when you're negotiating the functions that go across a connector, like a PCI Chem connector that already had legacy functions on the pins. For example, on the PCI Chem, the JTAG pins were rarely used through a bunch of surveys, mostly in a manufacturing situation, but they weren't used so they're kind of wasted in real time. So that was a situation where we were able to flex in without breaking backward compatibility the USB interface. But it also, that's an easy one in terms of through discover and then comparing the compatibility of the system wiring and the add-in card wiring. But so that this concept goes all across the board in terms of understanding what you're coupled to, compatibility check, and then engagement of the function that you've agreed upon. So that's kind of a common theme, and we've put into the PCI base spec 6.2 those common sets of rules that we're now trying to build on top of as we're trying to make every wire as useful as possible and not just inert DC or toggles every once in a while. So that's a basic concept. PCI VDM, some companies love it. Like I said, some companies want to turn it off completely, say don't even talk to me about it. But they are leaving a lot of bandwidth on the table by not using that. So there's targets in the CPU. For example, you may not need the slow sideband interface into the CPU, such as I3C. You could talk PCI VDM straight to the CPU and get all the telemetry stuff you want. Further, the forwarding of the messages. This has been about a 14-year journey probably to get really the ecosystem of PCI VDM targets all there and CPUs that forward the messages across sockets reliably. So it's all there, but there's still this reticence to adopt it by some because of the security implications, peer-to-peer, access control limiting. So we're working with PCI SIG to try to improve these things, as well as I mentioned earlier, the robustness, broadcast limiting. So there's these situations deep in the PCI world of unsupported requests and things like that. If you do support it or not, or you didn't drop the packets like you were supposed to. So there's concerted effort to try to harden these things so that the control plane can never affect the data plane, as well as the, like I was saying, a lot of the security aspects are totally buttoned up. And then there's this effort, I'm just pitching this enhanced system firmware intermediary. It's a new ECN in the PCI spec that really is very interesting in terms of how you do hot plug. There's a lot more hot plug types of things happening. It's not just, it's moved on beyond the NVMe world, the OCP NICs, things of that nature are wanting to adopt a lot more hot plug situations. And this is a very interesting way to do key management and discovery and compatibility and right revving of firmware. For example, on the targets before you're allowed the OS to see those types of entities. So definitely encourage people to, I think it's out in a vote right now. It's not in a release version of the spec, but if you're a PCI SIG member. And then there's also ARM system ready. Historically, in the ARM world, going back to ARM servers in 2010, it's all been this SSIF, which is about I think it's a 400 kilohertz I2C bus for all host to BMC interfaces. Well, imagine the things that are happening here that you're wanting to exchange between BIOS, UEFI runtime services, and OS applications or whatever, that, that neck down. So we're working with companies like ARM for the system ready requirement and trying to make sure that even ARM SoCs can start to make that available as an option. So we're doing these through obviously all standard stuff. We're trying to flatten the get through some of these have been historically very contentious in terms of all the nuances that it takes to adopt some of these interfaces or converge. So the final conclusion after about a couple years of research was there is not exactly one that's going to solve everyone's problems, but there is a lot of opportunity here to do convergence of interfaces and still be able to get those performance gains and the fan out gains and things of that nature, like the multi-node scaling, for example. And we're working through PCI DMTF, to try to help fulfill this vision that's happening in all these standards bodies around the telemetry and the needs-driven applications, telemetry security, runtime security, all this sort of stuff that's needing to pump so much information all the time through these sideband interfaces. It's very, very different than 10 years ago, obviously, where you're just, it's just a temp sensor. I'm going to pull it every 5 seconds. So things have very much evolved. Very interested in people's opinions on these things, so that we're on, we don't have fragmentation that kind of causes pain when you're trying to achieve a lot of this interoperability. And we can all benefit from, it's a lot of it's non-differentiated, so it's really flattened across the, the customer's not buying your system because you have a faster sideband interface, but they will complain if it's not fast. So, definitely looking for the community to try to help. These are the kind of, we have this PCI protocol working group sideband subgroup every week where we talk through a lot of these things in the PCI world. No, this is fully, but on the OCP side, the DC-MHS, the plug and play. There's base specs that are showing a lot of options, and we've talked a lot today about design specs that narrow those options down to help have more consistency across bigger swaths of the marketplace and, get involved. So I'm going to double check these links before we upload this to the website before they publish it publicly, because I may have a couple mistakes in there. But any questions? Concerns? I'm really surprised if there's not, but that's okay. Just there's a lot there. We've tried to really take this holistic approach, try to educate people from a lot of experiences that people have had with these types of interfaces, and really not just ignore it and let us limp along for so much more with some of these legacy interfaces. Yes, we have backward compatibility things to always deal with. There's the easy path, but these use cases really are needing, very different thought processes and ability to go in. I think we put in one of the slides, if you're designing a new form factor, USB 3.1 would be great. Just forget about the 2.0. You don't need both like it's a Type A connector. So things of that nature, like PCI Chem, you couldn't add 3.1 because there was not a diff pair grounded, 2 diff pairs grounded near each other in the pinout that you could actually adopt that. But 2.0, it's not the best. Some of these things have warts. But it fit within the existing confines of being grounded and good signal integrity to be able to achieve that better bandwidth at the endpoints. Any other question or any questions? Thank you very much.